Hello, welcome to another lecture in the Computer Architecture course. In this course, we have been looking at various components that make up a computer. And in the previous weeks, we have looked at CPU, memory, input-output devices, and how they become the key components of a computing device. And from that, we also looked at how these things are interconnected or interfaced, and through interfacing, how various communications or low-level data transfer happens between these components. So from expanding from that, in today's lecture, we are going to look at communication. And here we are talking about any form of data transfer from one point to the other. So in the case of interfacing, it was about how data was communicated between or data transferred between the key components of CPU, input-output devices, and memory. And today we are just going to extend that into a further understanding of how these data communications can happen and some of the protocols that are relevant to that communication that happens in such computing environments. So what we can see here in this diagram is, or in this set of diagrams, is various ways communications can happen or various networking architectures that can be there. So in the first diagram, what we see here is we have a number of components that are trying to communicate with one another, and how they are doing that communication is through a shared memory. So here we would call this a shared memory based communication, and what happens here is whatever the necessary data transfer would happen through this shared memory. So things can write and read from this shared memory. So if we recall from the previous week, say an input-output device, whatever the information from the input-output device is loaded onto the memory, and then CPU is reading from that memory. This is something similar to that approach. Then in the second approach, what we have is, again, we have these components that need to communicate, but here the approach we have is we have a shared common bus, and the data transfer can happen again through this common shared bus. So this common pathway is shared across a number of devices. So again, this is similar to what we again looked at in the previous weeks of having, say for example, a data bus or an address bus or a particular purpose bus that is shared across a number of components. Then we have a number of approaches that may be also relevant in other type of communication environments. That is, we have a number of components, and now the connection or connectivity is based on how these things are connected. So these are connected to one another, and they can communicate through those direct connections. Say for example, P1 would be able to communicate to P3 and P2 through its direct connections. Similarly, P4 can communicate with P2 or P3. So that is a dedicated connection that we have to communicate between these devices. Then the other approach that we have is a common way to connect, but through some network. So an example that is shown here is through the internet. So again, we have these devices or these components, and then they need to communicate, and that communication is going to happen through the internet. So what we would have is we would have these necessary communication initiated into the internet, and again the other end would also connect through the internet. That is another way of communicating. Say for example, here it was direct connections, so things were connected to one another, whereas here things were not directly connected to one another, but they are connected through a common network, for example through the internet. So from that we can sort of categorize these basic network architectures based on these connectivities into two main categories. One is point-to-point networks and the other one is shared medium networks. Point-to-point network are devices or nodes that are connected to one another directly. So in the previous example, like P1 was connected to P2 and P3. So these are directly connected to one another and they can communicate with those directly connected nodes. The advantage or a good point about these is they are much simple and they are reliable because they are directly connected. There's no complication there. And they can also be advantages if having that direct or dedicated connectivity can be useful in getting certain advantages in terms of meeting real-time deadlines or certain requirements like that. But the disadvantage or the main disadvantage with this approach is they can be much costly if we want to establish connections to large number of nodes. Say for example, if you only have, let's say, 4 nodes, then each node needs to connect to 3 other nodes. So it may be okay. But say if we have, like, say 100 nodes, and if each of the nodes need to connect to 100 other nodes, then it is going to be significantly inefficient and also costly affair to implement something like that. Then an alternative approach or the other way of connecting these nodes could be through a shared medium. So that is like connecting through the internet, or like some form of a shared medium that all these other devices can connect to. So this may be also similar to the approach of having a common bus. So here nodes are connected to this common bus or some form of a common network. So the wiring that is needed is much less because they are only needing to connect to this common bus. So what we would have is, say, we would have this common bus and all the nodes can just come and connect to this common bus. Whereas in the case of the point-to-point networks, each of those things had to connect directly to one another. And the advantage is, say for example, if you want to add a new node in a point-to-point network, now we have to create connections to all the other existing nodes. Whereas in the shared media networks, what we need to do is we just need to connect to that common bus or that common network. By that we can easily connect to the network. But the disadvantage or the main drawback is that because of this shared medium approach, we will have to use some form of much more complex network protocol to decide who is going to use this shared medium, because all of these nodes can use the medium. So then there should be an approach to decide who gets to use it at what point in time. Then when we think about communication, we need to understand certain basic communication concepts and methods that can be used to connect computing devices. So the first way of identifying them is how a medium or how a communication wire is used. So whether it is simplex, duplex or semi-duplex. We'll look at that. So this is basically what is the directionality of the connection. So whether things can go in one direction or both direction, or how that works. So the directionality of the communication path. So that is about, say, if we can communicate in one direction or in both directions or both directions at once. Then whether we have a serial or parallel connection. So a serial connection is using a single or a few wires, whereas in parallel connection we'll have to have a large number of wires corresponding to the number of bits that are there. So you may recall what we looked at in the previous weeks. Then we have synchronous or asynchronous communication. Again, this is relevant to how signaling can be happening from one node to the other. So synchronous meaning the nodes at both ends need to be at the same time scheme so that they can send and receive without any issues, whereas asynchronous meaning they can send without having that common time understanding. Then one of the common things of all these communication approaches would be data throughput. So there, what we would be interested in is what is the amount of data that could be sent through the network over a period of time. So here, in terms of the directionality, what we can have is simplex, half duplex or full duplex. So when we say simplex, it is basically that communication medium is only able to send data in one direction and not the other way around. So things can go from one to the other, but the other direction will not be allowed. Then a half duplex connection is data can flow in both directions, but only in one direction at a particular point in time. So this can send in this direction, and after that maybe this can send in this direction, but not both at the same time. Then the third approach is what is called full duplex. Here both the directions can communicate at the same time. So this can send at the same time, this can send, and likewise. So the main difference between half duplex and full duplex is in half duplex only one direction can be accommodated at a particular point in time, but both directions can be communicated using the same lines, whereas in full duplex we will be able to do that at the same time. So in terms of, based on this, we can sort of categorize the type of data transmission that we may have in as shown in this diagram. So what we will have is, we can initially categorize things as parallel and serial. Then within serial we will have the asynchronous and synchronous parts. So the reason for that is, if we are using parallel lines, then whatever that we signal here can be directly received here at the same time. So all the data transfer will happen at the same time. So there is no time delay in terms of bits. So we set all the bits here, then we read all the bits here. So it can happen at the same time in a parallel transfer. Whereas in a serial transfer, what we would have is, we will have to send one after the other a series of transfers. So when things are sent from one end, they need to be received at the other end with a particular understanding as to how long a particular bit is going to be transferred. So say if we are sending 4 bits over a period of time, the receiver should know at what point in time it has to stop and read the next bit. So if every bit is coming every 1 second, it has to read every 1 second. If every bit is coming every half a second, it has to read every half a second. So that understanding is necessary in serial communication. So based on that, we have two approaches. One is synchronous and asynchronous. In synchronous, we will send these bits at a particular fixed interval of time. In asynchronous, we will be sending things in a random order, or like there's no set time interval that we will have to keep up to. So now, if we go into parallel communication a little bit further, the main thing here is the interface is able to transfer multiple bits at the same time. So what we would have here is, we would have a number of bits that needs to be communicated, and the same number of bits will need to be received at the receiver's end, and all of them will be communicated at the same time. So there's no time delay in between the bits. All the bits are communicated at the same time at once. So not like one bit after the other. All of them are together and sent across from input to output. So what we would have here is, or what we would need here is, a bus of wires. So we looked at what a bus is: a group of wires, group of parallel wires. So for parallel communication, what we would need is a bus of wires that are connected between the both nodes or both ends, and this can be, say, 8 bits or 16 bits or whatever, depending on the bus width of the communication that we are implementing. The main advantage is this is going to be fast because all the bits are communicated at once. There's no time delay in between bits. It is straightforward because, again, there's no complication in terms of when the next bit is going to come and so on. And as such, it is also fairly relatively easy to implement. Again, there's no need to understand when the next bit is going to come, at what point to read and whatnot. Everything is sent at the same time, received at the same time. But the problem here is, or one of the main drawbacks with parallel communication is, it would require more input-output lines. Say, if we use a 16-bit line or 16-bit parallel communication, then that would mean the input-output lines there we would need to have 16 wires. So that would make the type of communication or the type of device or the cablings and so on much larger in size, and the devices can also become larger because of that particular reason. So in addition to the data wires, we may also have some additional wires such as control wires and sometimes even other power wires and so on. But the main idea is there would be 1 bit per wire. So we would have that number of data wires, but in addition to that, we may have few other types of wires as well in a parallel communication. The main advantage that we would have here is we have high data throughput. So what we have is, we would be able to send high number of bits within a short period of time, but it is only applicable, or the only possibility is across short distances because of the bulkiness and needing the large number of wires. We may only use this in short distances, but in short distances it is able to send a large number of bits within short period of time, so hence having high data throughput. So this is mainly used in sort of internal, when we think about computers and computer architecture, this is mainly used in connecting the key components. Say, for example, we may connect a CPU and a memory through a parallel bus, or we may connect such components within a computer environment through parallel communication. The other key thing to note is, because of the bulkiness and the high cost involved, these are very much limited to being used in short distance applications, and we would very rarely see any possibility of using parallel communication in sort of long distance communication. It's not to say that it's impossible, it is more like impractical to use parallel communication across long distance. So, on the other hand, if we think about serial communication, here what we have is, for example, we would have one data wire, and that is going to send one bit at a time. So, what we have here is, we have a single line that is sending data across, and it has to send one bit after the other. So, and at the receiver's end, it is going to receive one bit after the other. So, there's going to be significant delay compared to parallel communication, where all the bits were sent at once. Here we will have to wait and send one bit after the other. So, and the basic necessities, we should have at least one wire to send a serial communication. But again, as with parallel communication, we may have additional wires to do other things like sending clock signals and so on. So, if we think about serial communication, the main advantage is this can be used across long distances without any problems. We can send large number of data across long distances, and it is much cheaper and would be less bulky compared to parallel communication. But the problem with this approach is, the advantages are it's cheaper, less bulky compared to parallel and all, but the main sort of disadvantage or the drawback here is, we need to have much more complex communication protocol and also possibly hardware to support this. So, what we mean by that is, the sender and the receiver both need to understand how to decompose the message and send, and then receive the message and recompose it. So, for example, say if we are sending these 4 bits, what we will be sending is 1, 2, 3, 4 bits at a time. So, one after the other this will be sent, and then the receiver will receive one after the other, and now the receiver has to decide how to build that 4 bits back again. So, there will be additional protocol complexity in terms of using it or implementing it when we have serial communication, even though it has the advantages of being cheaper and less bulky in terms of the hardware implementation. So, within serial transfer, we said we can categorize that into synchronous serial transfer and asynchronous serial transfer. So, the point being, in synchronous serial transfer, what we would do is, we would have a set time interval to send set type of words or set length of data. So, we would have a set length of data, and we would send that within the same time frame across the communication medium. So, we would keep this constant across from sender to the receiver. On the other hand, what we have is asynchronous data transfer. Here, we don't have to continuously send things. We can start and stop the sending at any point in time, but so how do we manage that is we will have to have some form of starting bit and stopping bit to indicate that the data transfer is starting and data transfer is stopping, and we may have additional points in time where we are not sending any data. In synchronous, we were always sending some data and that has to be filled with continuous data flow, whereas in asynchronous data transfer that is not the case, but we will have to dictate or demarcate the start and ending of the data transfer using start and stop bits. So with that, if we think about the advantages of serial communication over parallel communication, the main advantage is serial communication requires few interconnecting cables. So it doesn't require many cables to do the connectivity. It can essentially work with one or two wires, maybe few more, but significantly less number of wires compared to parallel communication. So it requires less space to physically locate them in terms of the ports or cables and so on. And it also has the advantages of, because we don't have a lot of wires or cables having, then there's no issue in terms of signal interference, crosstalk and so on, because of cables having magnetic interference and so on. So that is also not there in serial communication. And the other advantage is, because of these reasons, it can also be much cheaper to implement because of the less hardware necessity and so on. It can be much cheaper in terms of physically implementing it, and it can also be possible to have such interfaces or ports in much smaller devices. So because like again say if you want to have like a 16-bit parallel port, then we need to have 16 pins there, whereas with a serial port we may not need that many number of pins. So there are such advantages in serial over parallel communication. So if we think about serial communication, there are a various number of communication protocols that can be used in computers and control systems and things like that, which can be used to implement various types of serial communication. So some of the examples can be UART or SPI or I2C, CAN, USB one wire, and these are some examples of serial communication. And one of the most famous serial communication protocol that you all would know is USB, or the Universal Serial Bus. It is a serial communication protocol. So that is one of the most commonly used serial communication protocol in many types of computing devices, and you may have some devices lying around you even at this particular moment. So from that, we can also think about certain other additional communication principles. So one of the common approaches that we would have in building communication protocols and building complex communication systems is the approach of building layered systems. What we mean by that is we would be building systems with multiple layers and each layer doing different things. So we would have a high level layer that would do the software or like protocol decoding and encoding part, where we would have a low level layer that is doing the actual signaling of electrical signals, generating the signals and so on. And we can divide these different functions of the protocol into different layers, so they can be managed independently and they can be designed in a much more elegant manner. And then we would also have parallel and serial communication and also wireless communication as well. We'll look at some protocols to each of these in the coming sections. So when we think about layered communication, you will be studying about this, or you may have already studied this in your networking course or data communication course. But just to recall, what you would be doing is, what we would be doing in a layered approach is, we would divide the communication protocol into a number of layers doing different things. Say for example, at the physical layer, what we would be doing is, we would be thinking about the physical communication. So that is sending bits from one end to the other. That physical communication would be dealt at the physical layer. Whereas on the top, at the application layer, it would be the data communication application. So for example, what happens when a browser is generating a network request. So that would happen at the very top layer, and the physical layer would do the low level part, and then there may be a number of other layers in between as well. So this would eliminate and make it much simpler in terms of a design task. So, and it can also help in interchanging certain aspects of a protocol with different possibilities. So this is something that you would study in much more detail in your data communication course, but this is just to remind you that this is also an approach relevant to communication in computers. Then, as we said, parallel communication has some advantages over in short distances, giving higher data throughput. So it would be used in interconnecting ICs or chips with the key components within a computing device. But the disadvantage is it can be high cost and also bulky because it uses one bit or one wire per bit of communication. On the other hand, serial communication can happen with just a single data wire, and it can be used across long distances. It can be cheaper, it can be less bulky, and also it can be much cheaper and less bulky. So it can also be, the size can be small, so it can be fitted into smaller devices as well. But on the other hand, we may need much more complex protocols to enable serial communication. And on the other hand, wireless communication is where we would be communicating without any physically connected wires, but using some form of radio waves or some form of waves, things like infrared or radio frequency. We would communicate through such electromagnetic waves. So here again, we would have a number of different protocols doing various things. In the case of infrared, that is something that you may even find in your TV remote. That's an infrared remote controller most of the time. So it is sending a pulse of a light and from the remote, and the TV is receiving that pulses, and it is decoding that into a data stream. On the other hand, radio frequency, say for example you have Wi-Fi or something similar to that, where you are sending and receiving data through a radio frequency signal. So one of the things to remember is data communication protocols can be significantly complex in terms of how many are there, and in the purpose of this course is not to study these communication protocols, but to give you an understanding that there is a significantly varied type of communication protocols. So that's what we are doing here, and we will be studying about these things in much more detail in various other courses such as data communication or even operating systems and so on, that may be coming in your future semesters. So what we will now look at is some examples of such communication protocols, just to give an understanding of how these protocols work. So the first serial protocol that we will look at is I2C. This is a 2-wire serial protocol. So what that means is we only need 2 wires to communicate. So we said sometimes we can do with 1 wire. So here we need 2 wires to communicate, and this is mainly used in embedded systems or similar systems where a simple data communication protocol is needed. It has limit in terms of the amount of data transfer rate, because it is a single wire protocol or 2-wire protocol. The data transfer rate may be limited, but it is a simpler protocol to use in many embedded applications or simpler communication needs. So what we have here is a way how this protocol is going to work. So what we have is we have 2 wires connected, so that those 2 wires, and whatever the devices that need to connect will connect to those 2 wires in parallel. So like connecting through a bus. So this connectivity is similar to connecting through a bus, and all of these devices will also have their own addresses. So each device will have to be given an address so they can communicate at a particular point in time. So then this timing diagram shows like how the communication happens in terms of starting, sending and stopping. So that is basically I2C. It is a basic simple serial communication protocol only using 2 wires, and even though it doesn't have much higher data throughput, it is still usable in basic embedded applications or applications that does not need higher data throughput. Another serial protocol example is what is CAN, which is a control area network, which is commonly used in a lot of control systems and things where they build real-time applications. So things like elevators, lifts, or production lines, or things like that. Again, a serial protocol, things are connected through a serial protocol, but here we have much higher data throughput compared to say I2C, for example. So different protocols will have different data rates and so on. So depending on the application, we may be able to choose between one or the other in terms of the available protocols, even though all of them are still serial protocols. One of the most common serial protocols that we would come across is USB. So this is one of the most common ones that's used in computing applications, mobile applications and many other applications. And various different versions of USB have various different data throughput rates. Some of the recent USB version 3, 3.1 and so on have much higher data throughput rates, and they can provide power to devices and so on. So there are various possibilities in terms of using USB. And one of the things about USBs is USB has what is called a USB host controller. So what is possible is, say for example, you may connect to a number of devices through a USB, and then you connect that to a hub, and then you can connect further number of devices through that hub, and so you can daisy chain and so on. So that is one of the things that can be done in USB, and that is one of the things that you would come across in your daily life much more than any other serial communication protocol, for example. And then when we think about parallel communication protocols, we have, as we said, parallel communication protocols are going to be mostly used in internals of computing devices, hence the example of PCI buses. So these are communication buses that exist within computing devices, so they are parallel communication protocols. So a peripheral component interconnect, PCI bus, and various iterations of it are parallel communication protocols. So they are mainly used to connect chipsets, expansion boards, and other memory subsystems. So again, computer internals, and they also, particularly in the case of PCI bus, it uses multiplexed data address lines. So again, if you recall from the previous lesson of interfacing, we may be able to use some bus lines to multiple functions. So here it can be multiplexed for data lines as well as address line at different times. So that is an approach that we can take in parallel communication. So that is something again used in general computing applications. Then in terms of another parallel communication protocol that may be common is ARM bus, which is again used in ARM processors, ARM Cortex processors, which are commonly used in embedded systems or mobile devices. So they have their own parallel communication protocol. So again, here still it is an internal or like close to processor. So that type of a communication that we are talking about. So that is again another example of a parallel communication protocol. Then if we think about wireless communication protocol, we talked about infrared, and one of the infrared protocols is IrDA, which is Infrared Data Association. It is a data communication protocol using infrared. Again, it may be not so much used these days because infrared is not the preferred way of communication for these type of devices anymore, but it can still be used, and it is an example of using a wireless communication through light or through electromagnetic waves. An example of connecting cameras and cell phones and so on, that is a possibility. But one of the most commonly used wireless communication protocol that you may be familiar is Bluetooth. So it is a low-cost device to build short-range radio links. So for example, you can connect your phone to the computer, an earphone to the computer or the phone. So these can work within short distances, but there's no need for having line of sight, whereas with infrared, that data communication needed to have line of sight. So for example, if you think about your TV remote, you have to point the remote at the television to get a command going to the television, the data transfer going to the television. Whereas Bluetooth, it doesn't have to be like that. Say for example, you can use your Bluetooth earphone in your ears and you can have the phone in your pocket. It would still work without the direct line of sight. And this is one of the current sort of common standard for mobile sort of wireless connectivity. Even though it's an old protocol, it is still with new variations of Bluetooth 4.0 and 5.0 and so on. It is still a most commonly used wireless protocol. And one of the other wireless communication protocols that you would be again using a lot is Wi-Fi, or a number of variations of Wi-Fi, IEEE 802.11. So this is the wireless LAN protocol. So again, this is something, if you recall the layered communication approach, we had the physical layer and so on. So what we have is, in that physical layer, we can have wired connections or we can have wireless connections. So we can have a wired Ethernet connection there, or we can have a wireless LAN connection there. So that is the Wi-Fi connection that you may be familiar with. And again, here we can have various data rates depending on various versions or iterations of the protocol. But the main thing to remember is that is a wireless communication protocol that you may be using in computing environments. So with that, we come to the end of communication. So this is just an extension to our discussion in interfacing in the previous week, and we will be continuing our computer architecture discussion in the coming weeks as well. In the meantime, if you have any questions about this particular lesson, please let me know through your LMS or other communication methods. And also, if you have any particular feedbacks about this lesson, or if you have any comments, please let me know them as well. Other than that, that's the end of the lesson. See you next time. Thank you. Bye.